Every lathe in every shop on Earth today has a slide rest on it. A tool held in iron, moved by a screw, cutting to a depth you dial in rather than a depth you feel. Before 1800, that did not exist. The tool sat in a man's hands, braced against a rest, and the accuracy of the cut was the accuracy of his wrists. One shop in London changed that. The man who ran it was the finest hand craftsman in the country, and he spent his career building the machines that made his own skill worthless. This is Trade Archive. 6 men built modern precision, one capability at a time, and this is the second of them. Hit like and subscribe, because the ceiling this man broke is the reason there are tolerances on your drawing at all. Woolwich, 1783. Inside the Royal Arsenal, a 12-year-old boy is filling cartridges for the artillery because his father is 3 years dead and the household needs the wage. Henry Maudslay had been born a short walk from those gates, on the 22nd of August, 1771, in a 2-roomed wooden house in Salutation Alley. His father had served in the Royal Artillery, was wounded out of it, and finished his working life as a storekeeper and artificer inside the arsenal itself. He died in 1780. Henry was one of 9 children in a house that suddenly had no wage coming into it. 2 years on the cartridges, then a spell in the carpenter's shop, and at about 15 he got onto the blacksmith's floor, which is where he stayed. Forge work at Woolwich meant gun carriages, fittings, hand tools, all the ironmongery an artillery establishment eats through, and Maudslay went straight for the delicate end of it. Samuel Smiles, writing in 1863, records the small iron trivets he made as a boy to show what he could do at the fire. John Wilkinson had already proved, with a bar run clean through a cylinder and carried in bearings at both ends, that a machine could hold a datum better than a workpiece could. That single idea made the Watt engine commercially possible. But it stopped there. Wilkinson could produce one accurate hole and could not produce 2 identical ones on purpose. There was no instrument in Britain that could read what he had made in any language finer than the thickness of a coin. No gauges, no reference surfaces, no standard thread, nothing to work to. Every part in every shop was still married to the part next to it, filed and tried and filed again until the 2 of them agreed. That is the ceiling. And the man who broke it started by picking up a file. At 18, Maudslay was recommended to Joseph Bramah, an inventor in London who had a problem. Bramah had patented a lock in 1784 that worked on a set of sliders, each of which had to be pushed to its own exact depth before the bolt would move. Get one slider wrong by a hair and nothing happens. The security of the whole design lived in the precision of parts smaller than a fingernail, and the men available to make them were men with files. Rowe, writing The History of the Trade in 1916, tells the story of Maudslay's interview. A worn-out bench vise, restored in a single day, the jaws re-steeled, trued, recut, and hardened, and that was accepted as his credentials. Bramah put him on lock work. Maudslay's real work there was the machinery behind the locks, a set of purpose-built tools to produce the exact parts the principle demanded, in quantity. The Science Museum, which holds the challenge lock today, records that Maudslay made it in 1790, and that he was chief engineer at Bramah's from 1789 to 1797. The challenge itself was a piece of theater. The lock sat in the window of the Piccadilly premises under a card offering 200 guineas to any artist who could make an instrument that would open it. Nobody could. When Hobbs finally did it in 1851, Bramah's firm argued about the terms for years afterward and pointed out, not unreasonably, that a lock which takes a specialist 16 days and a custom toolkit to open is not a lock anyone is going to defeat on a doorstep. Hobbs got his 200 guineas, paid over as £210. The other job at Bramah's was the hydraulic press. The physics was Bramah's, and it was sound, but the press leaked at the piston, and a press that leaks is a press that does nothing. Rowe records that the solution was suggested by Maudslay. A leather cup fitted round the ram so that pressure got underneath the leather and bellowed it outward against the bore. The harder the press pushed, the tighter the seal became. That cup seal is still the standard way to seal a hydraulic ram. By 19, he was running the shop. He married Brahma's housemaid, Sarah Tyndall, in 1791. He stayed the better part of 9 years, and then he asked for a raise above 30 shillings a week, was refused, and walked out. He opened his shop off Oxford Street in 1797, later moving to Margaret Street in Marylebone. His first customer, by Rowe's account, was an artist who wanted an iron easel. Now, the screw. Understand what a screw was in 1797. It was a spiral filed or chased into a cylinder by hand, by a man following a mark, and no two of them agreed on anything. Pitch wandered. Threads ran sloppy or tight along their own length. There was no such thing as a nut you could take off one bolt and put on another. And there was no such thing as measuring a distance by counting turns, because the turns were not the same size. Maudslay's first method was crude, and it was clever. You take a soft cylinder of wood or tin, put it between centers, and set a hardened crescent-shaped knife against it at a precise angle. As the cylinder turns, the angled edge walks itself along and cuts a continuous, even spiral. The pitch comes from the angle of the knife, not from the hand of the man. That gets you a screw. It does not get you a good one. What Maudslay did next is the actual genius. He took the best screw he had, mounted it in the machine as a guide, and used it to cut the next one. Then he tested that one, corrected it, and used the corrected screw to cut the one after that. Each generation carried a little less error than the one before, which means the accuracy was not found anywhere. It was manufactured, deliberately, by a process. Holzapfel, who documented the method, describes the perseverance involved and the result. A brass screw about 7 feet long, so close to true that when Maudslay checked it against standard measure and found it long by about 1/16 of an inch over the run, he built a compensating slide to pull that error back out, so the traverse came to exactly 7 feet. That is the hinge of the century. He was correcting a machine against a standard, in fractions of an inch, over 7 feet, in about 1800. Wilkinson, 25 years earlier, was describing the best work in the world in terms of the thickness of a sixpence. Every method of measuring small distances that a shop has ever used comes back to a screw. A micrometer is a screw of known pitch and a barrel divided into parts of a turn. A dividing engine, which is how graduated scales and gear teeth get laid out in the first place, is a screw driving a table. A measuring machine that checks a standard of length against a master is a screw. The lead screw on the lathe is a screw. Fix the screw, and you have fixed the ancestor of every measuring instrument that comes afterward, which is why the problem occupied instrument makers and engineers for the next 100 years, and why the accuracy of a screw's pitch remained the limiting factor in measuring anything. Maudslay also rebuilt the tooling that put threads into holes. His taps cut instead of squeezing, carried 3 cutting edges, and came in a graduated set of 3, taper, middle, and plug, so that a hole closed at the bottom could be threaded to full depth. Holzapfel notes that tapping a dead hole in cast iron with a full thread had been effectively impossible before that. The lathe that all of this ran on survives at the Science Museum. It is built on 2 parallel triangular bars. One of them carries the headstocks holding the work. Between them runs the lead screw, geared to the mandrel through a set of change wheels, so that for every turn of the work, the tool advances a known, chosen distance, and changing the gears changes the pitch you cut. Riding on both bars is the slide rest, holding the cutting tool in a screw-fed slide with a micrometer dial to set the depth of cut. Anybody who has ever hung a gear train on an old English lathe already understands what that means in practice. You are not cutting a thread. You are choosing a ratio. The lead screw has a known pitch. The work turns at whatever speed you please, and the gears between them set the relationship between the two. Swap a wheel, and the pitch changes to another exact figure, not to whatever the man's hand happened to produce that afternoon. The thread becomes an output of arithmetic. Once that is true, the same thread can be cut again next year by somebody else on the other side of the shop, and it will be the same thread. The tool is clamped in iron, moving along planed surfaces at a rate set by gearing, and the man's job is to set it and turn the handle. Cut a thread on one rod, and you can cut 100 more the same, and the 100th is as good as the first, because nothing in the process depends on a man staying sharp through a long afternoon. Accuracy stopped being a personal quality and became a property of the machine. That meant it could be bought, crated, sent to Glasgow, and set up by somebody who had never met the man who built it. A shop no longer needed the best hands in England. It needed the right machine, kept true. Now, an honest word about who invented what, because machinists ask, and they are right to. The slide principle is old. There is a screw-cutting lathe with slide rests and a lead screw drawn in a German housebook from around 1480. Leonardo sketched screw-cutting machines with lead screws and change gears. Jacques de Vaucanson built an all-metal slide rest lathe around 1751, and it was written up in the Encyclopédie. Jesse Ramsden had a screw-cutting lathe by about 1775, which he used to make his dividing engines. There is a French lathe by Senot, dated 1795, still sitting in the Musée des Arts et Métiers, with change gears and a lead screw, built before Maudslay opened his doors. Maudslay's claim is not that he thought of it first. His claim is that he made it rigid, made it accurate, built it in iron instead of timber, put the three elements together in a form that held up under a heavy cut in a commercial shop, and then trained the men who spread it across England. Rowe notes that for years afterward, the slide rest was known in English shops as Maudslay's go-kart, which brings us to the moment somebody bet a war on it. The Royal Navy ran on pulley blocks. Every sail, every yard, every gun tackle went through them. A single ship of the line needed around 1,000, and the fleet was getting through more than 100,000 a year, every one of them cut and shaped by hand by skilled blockmakers. A block is not a simple object. There is a wooden shell, mortised out inside to take one or more sheaves. The sheaves are discs that have to be bored dead central and run true. The pin they turn on has to sit square. The shell has to be scored round the outside for the strop that holds it to the rigging, and the sheave bore has to be coked, which means fitting a metal bush into the timber so the thing does not chew itself apart under load. Get any of it wrong and you have a block that binds, or splits, or dumps a spar on the deck in a gale. Mark Isambard Brunel had patented machinery to do all of that. Samuel Bentham, the Inspector General of Naval Works, had the authority and the appetite to try it, and in August 1802, the Admiralty let them proceed at Portsmouth. Design work came from Brunel, from Bentham, and from Simon Goodrich, the Navy Board's mechanist. Brunel's patent drawings showed timber-framed machines. Maudslay threw the timber out and built them in cast iron, slimmer and far more rigid, and that decision became standard practice for machine tool construction from then on. He built accurate scale models first, which are now at Greenwich. The metal mattered for the same reason your machine has the mass it has. A timber frame moves. It flexes under the cut. It soaks up damp and dries out again. It shifts with the season, and every one of those movements comes out in the work as an error you cannot see and cannot correct. Cast iron is stiff, it is heavy, it damps vibration, and once it has been planned true, it stays where it was put. Iron frames stay where they are put, and repeatability was the point of the exercise. The first set went in during January 1803, the second in May, the third in March 1805. When it was finished, the block mills held 45 machines of 22 different types, driven off 2 steam engines of 30 horsepower each, arranged in sequence so that timber went in one end and finished blocks came out the other. In 1808, the mills produced 130,000 blocks. Historic England, in its report on the site, records the claim made at the time. 10 unskilled men working these machines could replace 110 skilled blockmakers. There had never been anything like it anywhere on Earth. A line, in sequence, steam-driven, built from all-metal machine tools, each one doing a single operation to a fixed standard over a century before anyone in Detroit drew a plan. The machines themselves were specialists. Saws that cut the shells to length and crown saws that cut the sheaves as discs. Boring machines for the sheave holes and the pinholes. Mortising machines that chopped the slot through the middle of the shell. Shaping engines that cut the outside profile. Scoring engines that cut the groove for the strop. Coking machines that seated the metal bush into the sheave. Each one did a single operation, held to a single setting, and the next machine in the line could rely on what came out of the last one. The standard lived in the setup of the machine rather than in a foreman's head. Your fixtures exist for the same reason. The men who had spent their working lives shaping blocks by eye understood exactly what that meant for them, and they were right. The Admiralty, being the Admiralty, then argued about the bill. Brunel was to be paid on the basis of 1 year's savings from the machinery, calculated at £17,093. He got £1,000 on account in August 1808 and waited roughly 2 years for the rest. Maudslay was paid £12,000. The capital cost of the whole installation came back in about 3 years. The machines stayed in service. Blockmaking at Portsmouth on Maudslay's machinery only stopped in 1965, and a number of the original machines survive today, split between the Science Museum and Portsmouth itself. Enter Joseph Clement, and hold that name. Clement was born in 1779 at Great Asby in Westmoreland, the son of a hand-loom weaver who owned a lathe. He worked as a thatcher and then a slater. With the village blacksmith, he built himself a lathe and used it to make flutes, clarinets, and bagpipes. He taught himself drawing. He worked his way south through Kirkby Stephen, Carlisle, Glasgow, and Aberdeen, reached London, worked for Alexander Galloway, then for Bramah, and rose to be Bramah's draftsman and superintendent. In 1815, he came to Maudslay as chief draftsman. He was two things at once, and that combination barely existed at the time. He was a toolmaker of the first rank, and he was a first-rate draftsman, a man who could both specify the work on paper and produce it at the bench. He set up on his own and started inventing a drawing instrument and a drawing table of his own design, improvements to the self-acting lathe, the double-driving center chuck and the two-armed driver, which let a workman turn a shaft the whole way along without stopping to reverse it in the chuck, fluted taps and dies, cut to the thread sizes he had learned at Maudslay's bench. Then he built the Great Planer. It was described to the Society of Arts in 1832 from his own drawings, took work 6 feet square, ran by hand, and could plane circular, spiral, and conical surfaces as well as flat ones. For more than 10 years, it was the only machine of that size in the country. It ran night and day on jobbing work, and Clement charged by the square foot for the privilege. That planer was his principal income for years. In 1823, Charles Babbage hired him to build the difference engine. Clement built the demonstration piece, roughly 2,000 parts, finished in 1832, and it stands as one of the finest examples of precision manufacture of the period. Then the relationship collapsed over money. Part of it was the cost of moving Clement's workshop closer to Babbage's house. Part of it was the trade convention that a workman kept the tools he made on a job, and Clement had made a great many expensive tools. Babbage came to believe he was being farmed for delay and unnecessary refinement. Clement knew exactly what his work was worth and billed accordingly. That is the kind of number that makes accountants cry, and in 1833, Clement walked. The engine was never finished. He died in 1844. The reason he belongs in this episode rather than in one of his own is that everything he became in 2 shops, and one of them was Maudslay's. Back at Lambeth, Maudslay had moved in 1810, out of Margaret Street with about 80 men, and into an old riding school on Westminster Bridge Road. He took Joshua Field, a former Admiralty draftsman off the Portsmouth job, as his partner. The firm became Maudslay and Field, and later Maudslay, Sons and Field, once Thomas Henry and Joseph came in, and it dominated marine engineering for the rest of the century. It engined the Great Western in 1838. It built engines for HMS Rattler and for the Royal Yacht, and patented the Siamese twin-cylinder engine in 1839. By 1900, something like 658 vessels had gone to sea on its engines. The patents in Maudsley's own name show a man who could not leave a problem alone. Calico printing machinery in 1805 and again in 1808. A differential motion for raising weights, taken out with Brian Donkin in 1806, which could also be applied to driving lathes. The table engine in 1807, a compact self-contained steam engine that stayed a favorite for small power for the next 40 years or so. He worked on distilling drinkable water from seawater for ships' boilers, and on stopping the scale that built up inside them. When Mark Brunel needed a tunneling shield for the Thames Tunnel, an iron structure of around 80 tons and roughly 36 feet across, it was built at Maudsley's works and lowered into the shaft at Rotherhithe in 1825, along with most of the tunnel's pumping machinery. But the most important thing about that shop was the standard maintained inside it. On a bench in Lambeth sat a measuring instrument the men called the Lord Chancellor, because when two workmen disagreed about a dimension, its ruling was final and there was no appeal. It worked on a screw cut at 100 threads to the inch, read against an index wheel divided into 100 parts, which resolves to a 10,000th of an inch. Maudsley built it around 1805. In 1776, the best engineers in Britain described the finest bore ever cut by reaching for a coin in their pocket. Inside 30 years, there is a bench in Lambeth where an argument between two fitters gets settled to 0.0001 of an inch by a machine in the afternoon without anybody writing a letter about it. That instrument did something to the trade that is worth being honest about. A shop where the measurement is objective is a shop where a man's judgment matters slightly less every year. Skill does not disappear. It moves. It moves off the file and into the setting of the machine, into the making of the gauge, into the man who builds the tool rather than the man who runs it. Maudsley's own life is the proof and the cost of it. He was the finest handworker anyone in London had seen, and he spent his career building the machinery that made that kind of handwork unnecessary. Nobody in that shop seems to have thought it was a tragedy. They thought it was the job. Every thread in the works was cut to his own sizes, from his own taps and dies. A bolt made in one corner of the shop fitted a nut made in another, by a man who had never spoken to the first one. Nowhere else in Britain was that true. Inside those walls it held, and it was the first working proof that the idea could work at all. The rules he ran the place by, Nasmyth wrote down. Get a clear notion of what you want to accomplish, and you will probably manage to do it. Watch your materials, and put the question to every pound of metal in the design. What business has it to be there? Avoid complexity. Make everything as simple as it will go. He was a big man, over 6 feet, wide across the forehead, remembered for a laugh you could hear across a shop floor. Everybody who worked beside him talked about his hands. James Nasmyth, who arrived on May 30th, 1829, at the age of 20, said it was a pleasure to watch him handle any tool at all, but that he was something else entirely with an 18-inch file. There is an irony in that which nobody in the shop seems to have dwelt on. The best pair of hands in London spent 40 years building the machinery that made hands like his unnecessary. Nasmyth's first job was helping the old man modify the screw-generating machine. He worked as Maudsley's personal assistant until the end, and almost everything vivid we know about that shop comes through him, written down half a century later by a devoted pupil who had become famous in his own right. The shop turned into a school, and the register reads like the founding roll of British engineering. Richard Roberts came down from Wales, dodging the militia on the walk, and worked as a fitter and turner from 1814 to 1816. What he took north was a conviction that handwork should be replaced by mechanism wherever mechanism can be made to hold the accuracy, and a set of rotary cutters he had seen in use on that floor. David Napier passed through. William Muir arrived just after the end. Joseph Whitworth came in around 1825 and carried out the surface plate, the scraper, and the discipline of standard sizes. That is the real output of the Lambeth Works. Not the marine engines, not the table engines, not even the block machinery. Men. By the middle of the century, you could walk into a serious engineering works almost anywhere in Britain and find a Maudslay man running it, or a man trained by a Maudslay man. The methods traveled through people rather than through publications, which is why they spread as fast as they did, and why nobody at the time bothered to write down who had originated what. It was how the work was done, and everybody who did it that way could tell you which bench they had learned it at. That end came in February 1831. Maudslay had been over to Boulogne to visit a friend, caught a bad chill on the crossing home, took to his bed at Lambeth, and did not get up again. He was buried at St. Mary Magdalene in Woolwich, a few streets from the Arsenal gates and the alley he was born in, under a cast-iron tomb he had designed himself. There is something exactly right about that. The boy from the forge, back in the parish he started in, under a casting he drew. Most of it is still here. The screw-cutting lathe is at the Science Museum. So is the challenge lock, and a Maudslay micrometer of about 1805, and a run of the original Portsmouth block machines. The scale models he built before cutting a single full-size frame are at Greenwich. You can stand in front of the iron and see the triangular bars, the lead screw, the slide. There is no reconstruction and no artist's impression involved. The objects survived because the people who owned them understood what they were looking at. So, what did he actually do? He took the cutting tool out of the human hand and bolted it to the machine. He made a screw true enough to serve as a master copy of length, then built the machine that could copy it. He gave the trade a bench instrument that could read a 10,000th of an inch and settle an argument on the spot, and he put reference surfaces on the benches where ordinary workmen could reach them. At Portsmouth, he proved that machines in sequence could outproduce craft labor by a margin nobody was prepared to believe until they saw the block piles. And here is where he fell short. All of it lived in one shop. The Lord Chancellor sat on one bench in Lambeth. The taps and dies were cut to Maudslay's sizes, which meant nothing in Manchester or Leeds or Glasgow. And the principle itself was still, in practice, one machine. The lathe had been solved. Planing, slotting, gear cutting, drilling to a fixed size, the whole family of machines a working shop actually needs, existed only in pieces, in one-off form, in a handful of private workshops belonging to men who had trained at that bench. Clement's great planer was the only one of its size in Britain for a decade, which tells you everything. It was a marvel, not a product. Somebody had to take what happened on Westminster Bridge Road and turn it into a shop floor. Somebody had to build the planer and the slotter and the gear cutter as ordinary production machines you could order, then run a works to templates and gauges so that any man on the floor could make a part that fitted a part he had never seen, made by a man he had never met. The man who did it walked to London from the Welsh border to dodge the press gang, spent 2 years at Maudslay's bench, went north to Manchester, and built the machines that everything after him was made on. That episode is coming up next.